Now it is with great pleasure that I introduce my friend and colleague, Dr. Dave Bushnell, the 2021 James H. Starnes Award recipient. Dr. Bushnell.
Thank you, Norm, for that most generous introduction. Can I be heard?
Yes, sir. We're at 53 participants now, Dave.
Oh, good. I am David Bushnell. First, let me thank AIAA and ASC for honoring me with the 2021 Jim Starnes Award. It was a real surprise. And thanks to AIAA for setting up this special session. In the title of my talk, shells is in quotes because some of the structures behave like shells, but are not shells. Much of this presentation is about the website called shellbuckling.com. Shellbuckling.com was created by my son Bill and me. Practically all of the images here are from shellbuckling.com. My son Bill is the webmaster of shellbuckling.com and is responsible for the overall organization and look of the website. I am responsible for its contents. In spite of the .com suffix, no money is involved. Access to the website is free. It will always be free. Nowadays, my voice is poor because I have a neurological condition that makes it difficult for me to control the muscles of the lower part of my face. That affects the sound of my voice. The condition is not life-threatening nor painful. Because of my involuntary head and mouth motions, I will now stop the video myself, which is distracting. Jim Starnes died in 2003. This is Jim in no, it isn't. I've got the wrong slide. Sorry. This is Jim in 1991. Jim was very interested in the buckling of shells. Jim's 1970 PhD dissertation at Caltech was about buckling and post-buckling of axially compressed cylindrical shells with cutouts. Here is one of his post-buckled test specimens. There are 3 parts to my talk. I want to finish my talk before I answer any questions. For slides such as this, I will pause for a while to give you a chance to read the slide. The first part of my talk is about classical buckling and post-buckling of imperfection-sensitive shells. An imperfection-sensitive shell is a shell whose maximum load-bearing capacity is greatly affected by the presence primarily of geometric imperfections. Please read the slide while I pause. This is Sir John Falstaff, a fictional character from William Shakespeare's play Henry IV. Notice that his boots have buckled. The upper part of his left boot has experienced very large, essentially axisymmetric deformation. The lower parts of both boots are in non-axisymmetric post-buckled states. Remember how his left boot looks. A few slides hence, we will see an actually compressed, rather thick, cylindrical shell in a similarly deformed state. At some time during their existences, the two toilet rolls at the top of this slide experienced axial compression strong enough to cause buckling and post-buckling of part of their surfaces. On the upper left side, the post-buckled part exhibits the well-known diamond-shaped post-buckling pattern of an axially compressed cylindrical shell. The roll on the upper right seems to have buckled axisymmetrically. Why the difference? Who knows? Maybe there's a PhD project in there somewhere. The roll at the bottom appears to have buckled from in-plane shear, that is, from torque. I swear I did not do anything to this roll to produce shear buckles. This is the way it came from the store. This important slide shows three types of post-buckling behavior. The upper curves show stable post-buckling for an axially compressed flat plate. The middle curves show neutral stability for an axially compressed slender column. The lowest curves show unstable post-buckling for an axially compressed cylindrical shell. The bifurcation buckling load corresponds to zero natural deflection. That is, in this picture, the pre-buckled state is considered to be undeformed. This is an important slide. Static load displacement curves are shown. The load, called lambda, is plotted on the vertical axis. The displacement congruent to the load is plotted on the horizontal axis. Curves like these might well represent the behavior of an externally pressurized shallow spherical cap lying on a flat surface. The nonlinear curve 0AC represents nonlinear axisymmetric pre-buckling behavior of a perfect shallow spherical cap. The point B represents a bifurcation point on the nonlinear equilibrium curve of the perfect shell. The buckling mode is called nonlinear because the nonlinearity of the pre-buckling behavior has been accounted for in the bifurcation buckling analysis. Along the downward sloping curve BD, the load decreases as the amplitude of the non-axisymmetric buckling mode increases and perhaps changes character because of nonlinear post-buckling behavior. Here we see the behavior of an axially compressed, isotropic, elastic plastic, rather thick-walled metallic cylindrical shell. This behavior is completely analogous to the behavior shown in the previous slide. The displacement axis is now called end shortening, which is congruent to the axial compression load. The nonlinear axisymmetric pre-buckling phase is represented by the two leftmost photographs. In this case, the bifurcation point B occurs, for example, after the limit load A rather than before A, as displayed in the previous slide. A post-buckled equilibrium state is shown on the lower right. Here, the post-buckling state exhibits very large deformation, very similar to the deformation exhibited several slides ago by Falstaff's left boot. Axisymmetric folds in the upper part of the cylindrical shell combined with non-axisymmetric folds below the axisymmetric folds. Here is another load displacement curve. This type of behavior is typical of a very thin-walled, isotropic metallic cylindrical shell under uniform axial compression, or a very thin-walled isotropic metallic spherical shell under uniform external pressure. The two dashed curves represent nonlinear behavior that would be obtained for a slightly geometrically imperfect shell. The maximum load-bearing capacity of the slightly imperfect shell is way below the theoretical bifurcation buckling load of the perfect shell. The perfect shell buckles at rho critical near the top of the pot. There's extreme sensitivity of the maximum load to a small initial geometrical imperfection, both for a cylindrical shell under axial compression and a spherical shell under external pressure. The top portion of this slide shows very thin-walled metallic isotropic buckled cylindrical and spherical shells. The cylindrical shell has buckled under axial compression. The spherical shell has buckled under external pressure. In both cases, there are buckles that are very small compared with the dimensions of the shell. Ordinarily, with a statically loaded shell under load control, one buckle would appear first, then the shell would collapse completely at a very slightly higher load. In a static test, you would not see buckles initially occur over a large part of the shell surface. In these two examples, there is a rigid mandrel inside each shell that prevents unlimited growth in the amplitude with the small buckles. The interior mandrels allow small buckles to develop all over the shell surface as the load is increased slightly above the initial bifurcation buckling load. The bottom portion of this slide shows data points that on the left side represent tests on axially compressed cylindrical shells with increasing radius to thickness ratio R over T, and on the right side represent tests on externally pressurized spherical caps of increasing depth. That is, increasing geometrical parameter lambda. Staying on the right side, for a given wall thickness, increasing lambda means deeper and deeper spherical caps. The deeper the cap, the more it behaves like a complete spherical shell. In both cases, the load-bearing capacity of actual shells, represented by data points, decreases with increasing travel along the horizontal axes. For high values of the horizontal axis, there's extreme sensitivity of the buckling load of actual fabricated shells to initial, primarily geometric imperfections. This slide shows post-buckled, uniformly axially compressed cylindrical shells. On the left side, we see an externally axially stiffened metallic cylindrical shell. On the right side, we see a laminated composite cylindrical shell. Notice that now the buckles are large compared with those for the thin-walled, axially compressed, unstiffened metallic cylindrical shell shown on the left side of the previous slide. The load-bearing capacities of cylindrical shells like those shown here are much less sensitive to initial geometric imperfections than for an unstiffened shell or for an isotropic metallic shell for the following reasons. One, the buckles are much larger. Hence, there are many fewer buckling eigenvalues slightly higher than the critical. That is, the lowest bifurcation load then holds for an unstiffened metallic shell. And two, Initial imperfections in the shape of the critical buckling mode are not likely to occur in as manufactured shells like these. This is an important slide. In both upper and lower images are plotted the knockdown factors, that is, normalized buckling loads, indicated by many experimental data points, versus the radius to thickness ratio, R/T, for actually compressed, unstiffened cylindrical shells. The upper image is for laminated composite cylindrical shells, and the lower image is for isotropic metallic cylindrical shells. The knockdown factor is simply the normalized buckling load, since the buckling load of the perfect shell is normalized to 1.0, as shown at the top of each vertical axis. There is a significant difference in the knockdown factors from the upper image, which is for laminated composite shells, compared to the lower image, which is for isotropic metallic shells. Practically all of the data points, that is the test results, in the upper image lie above a knockdown factor of 0.4, whereas in the lower image, many data points fall significantly below 0.4. This improvement in the behavior of actually compressed laminated composite cylindrical shells over that of isotropic metallic unstiffened cylindrical shells means that laminated composite aerospace cylindrical shells weigh significantly less than typical metallic cylindrical shells. Not only because composite material is stronger and less dense than metal, but also because the knockdown factors are significantly larger. This slide shows load displacement, that is load and shortening curves, for an actually compressed, internally actually stiffened cylindrical panel. Local buckling of the skin between adjacent stringers occurs at a significantly lower load overall, lower load than overall, that is general buckling. The load continues to increase as the depth of the general buckling deformation increases. It can be imagined that in this case, initial imperfections, that is both local imperfections and general imperfections with small amplitudes, would probably have little effect on the overall behavior shown here. This slide shows results for cylindrical shells under different loadings from axial compression. Loading by torque on the left side and loading by external pressure on the right side. The upper part of the slide shows shells buckled in general, that is, overall buckling modes. The lower part shows comparisons of tests versus theory, that is, data points from tests compared with solid curves obtained from theory. The values on the horizontal axis are the so-called Betzdorf parameter, which is a combination of shell length, shell radius, and shell wall thickness. Systems such as these are much less sensitive to initial imperfections than are actually compressed, unstiffened, isotropic metallic cylindrical shells. The least imperfection sensitivity is for cylindrical shells under torque, shown on the left side. Looking at the mid-range of Betzdorf parameter on the right side of the slide, the externally pressurized cylindrical shells exhibit somewhat more imperfection sensitivity than for the torqued shell, but still far less imperfection sensitivity than for actually compressed cylindrical shells. This ends the first part of my talk. Part 2 of my talk is about the shell buckling website, shellbuckling.com. I pause to let you read the slide. Shown here are my son Bill, the webmaster of shellbuckling.com, and I. This photo was taken several years ago in Yosemite National Park. Bill is responsible for the overall organization and look of the website, and I am responsible for its content. The website is a work in progress. I spend from 2 to 6 hours a day on this long-term project. From now on, Bill and I will release an updated shellbuckling.com about every 6 months. This is the home page of shellbuckling.com. Bill has placed all the clickable buttons in a column on the left side. In my talk, I have already covered the first few items, except you can help in news. This part of my talk, I will cover the 4 items, you can help, shell buckling bibliography, shell buckling people, and other buckling images. The glider shown here is making a tight turn around a mountain peak. Notice that the upper surfaces of the wings have buckled locally. The lift vector points toward us, so that the wings are bent toward us, upward in a structural sense. The curved upper surface of each wing near its root is subjected to significant span-wise compression, leading in this example to local buckling of the skin of the wing between adjacent spars. The glider does not fail because the bending load is carried by the spars. The skin exists mainly for aerodynamics. This type of early local skin buckling was shown previously for an internally axially stiffened, axially compressed cylindrical panel. There, as with the glider, local buckling between adjacent stringers occurred at a load significantly below that for general instability of the entire panel. On the home page of shellbuckling.com, the top button reads, "You can help." Listed here are several of the ways you can participate in the continuing development of the shellbuckling.com website. I pause to let you read the slide. This is the bibliography page of shellbuckling.com. There are 2 major parts of the bibliography page. The first part has 4 galleries of book cover images. These 4 galleries contain images of book covers for which the first author's surname begins with A through G, or H through M, or N through S, or T through Z. The second part of the bibliography contains the actual bibliography, that is, lists of citations of papers about shells. These lists of citations, which include abstracts and sometimes lists of references, are very long. There are 2 sections in this second part of the bibliography called Part 1 and Part 2. Part 1 presently has about 8,700 pages, and Part 2 presently has about 7,000 pages. Both parts contain the same kind of information. I just wanted to keep the number of pages less than 10,000. Therefore, some time ago, I started accumulating new citations in Part 2 of the bibliography. This is a sample screen from the book cover section of the bibliography. Shown here are 15 images of book covers, As shown at the top of the screen, this is index page 1 of 17 index pages. Each of these index pages has 15 images of book covers. All of the 15 times 17 book cover images are for books the first authors of which whose surnames begin with A through G, and I notice you can't see part of it because this is covering it up. I don't know how to lower the. How do I just lower the lower part? That didn't work. I just want the top. Well, I suppose it's here. I suppose that's acceptable.
You're good, Dave.
Well, I can't get it to cover. It's all right. It doesn't have to be perfect. No, that's not right. Well, let's forget it. What slide am I on? I'm on 22. This is the title of a very long 2 parts of the actual bibliography filled with citations of relevant papers. The scope of the shellbuckling.com website is not just buckling, but also vibration and dynamic response, and not just shells, but other types of thin-walled structures. The title reads, many references about buckling, wrinkling, crushing, crippling, crumpling, creasing, kinking, dimpling, folding, snapping, vibration, dynamic response, and optimization of membranes, films, sheets, plates, panels, shells, tubes, nanotubes, pipes, thin-wall beam columns, sandwich structures, and soft structures. Trying to get that green thing right. I think that's good. This slide shows the shell buckling people page of shellbuckling.com. As the clickable buttons on the left show, this section of the website is divided into 1 gallery of the deceased and 4 galleries of the living, people whose surnames begin with letters from sections of the alphabet, as with the book cover images. The deceased appear in order of the date of death, starting from members of the shell buckling community who died many, many years ago, and ending with those who recently passed away. This slide shows the earliest deceased members of the community. Here we see the portraits of people with familiar names: Galileo, Descartes, Newton, Euler, Lagrange, Laplace, Fourier, etc. The last index page of the deceased gallery has images of those who died most recently. For examples, here we see, among others, photographs of Johann Arbachs and Raphael Hafka. If you click on Johann Arbachs, you get the image on the next slide. You get a larger image and more information is shown here. This is a general capability holding for all of the galleries of images on shellbuckling.com. The living people appear in an analogous manner to the deceased, except that in each of the 4 living galleries, the images are ordered by the initial letter of the person's surname. Here we see the first index page of 27 index pages. Presently, there are 15 times 27 living people in the A through G shell buckling community. The other 3 living galleries, not to be shown here, are for researchers with surnames that begin with letters further along in the alphabet in a manner analogous to the book cover images. Notice the person in the lower left corner. On shellbuckling.com, there's a file about him, as well as all the other people. You can see this file is described in the next slide. On the Shellbuckling People page, there's text that lists all the people in the shellbuckling.com. There are 2 lists, one for deceased and one for living. Part of the living list is shown on the left side of this slide. You can click on any person's name in that list. Typically, here's what you see. For example, if you click on Professor Shandor Adeni's name, you get the image on the right. This is the Other Buckling Images page of shellbuckling.com. The other buckling images are divided into 11 categories, as listed in the column of clickable buttons on the left side of the screen. For example, the first 3 categories are unstiffened cylinders and plates, stiffened cylinders and panels, and non-cylinders. Each of the 11 categories follows the same format, that is 15 images per index page and a number of index pages, as that already displayed for book cover galleries and people galleries. This is the first index page of 28 index pages applicable to the first category, unstiffened cylindrical shells and plates. For example, we see at the lower left corner the same actually compressed, thin-walled, isotropic, metallic, buckled cylindrical shell shown previously. If you click on the image, on that image, you get the next slide. We see a larger image and more information is shown here, for example. This is the first index page of 15 index pages applicable to the second category, stiffened cylindrical shells and panels. For example, we see in the left part of the top row 2 of the stiffened cylindrical shells shown previously. This is the first index page of 16 index pages applicable to the third category, non-cylindrical shells. I don't know why this darn thing keeps moving. Good. Maybe it'll stay there this time. This is the first index page of 16 index pages applicable to the third category, non-cylindrical shells. For example, in the bottom row, second from the right, we encounter the image of the externally pressurized thin-walled buccal spherical shell shown previously. This ends the second part of my talk, part 2. Now I move to the last part of my talk, part 3. I pause briefly to let you read the slide. Here we see buckling of a thin-walled beam column with eye-shaped cross-section under a downward concentrated load P at its plane of symmetry. The beam undergoes downward bending so that the upper flange becomes axially compressed and buckles. There is also local buckling of the web directly under the concentrated load P at the plane of symmetry. There is, in addition, shear buckling of the web somewhat away from the plane of symmetry. Here we see buckling of an axially compressed column with cross-section of a lipped channel, depicted at the upper left. Shown here is the buckling stress as a function of the axial half wavelength of the buckling mode. Going from left to right, we see that there occur several different modes of buckling. 1. Short wavelength local buckling of each segment of the channel. 2. Medium wavelength, so-called distortional buckling of the entire cross-section. And 3. Long wavelength Euler buckling, Euler-type torsional buckling of the entire column in which the cross-section at any elevation rotates approximately as a rigid body. And 4. Longer wavelength Euler-type bending buckling in which the cross-section at any elevation translates approximately as a rigid body. This slide shows bending, A, and buckling, B, and forming of a carbon nanotube. One of the 11 categories of shells listed in the other buckling images page of shellbuckling.com is entitled nanotubes. A carbon nanotube is made by rolling up a graphene sheet. The type of single-walled carbon nanotube, often abbreviated as SWCNT, you get depends on the orientation of the atomic structure of the graphene sheet when you roll it up. In the literature, there are 3 types of SWCNT: zigzag, chiral, and armchair, as shown in the lower right part of the slide. This and the next several slides show several types of wrinkling of soft shell structures. Here we see wrinkling, that is circumferentially short wavelength buckling of an internally pressurized membrane indented at its pole. The wrinkles occur near the pole of the internally pressurized indented membrane because the membrane in that region experiences local circumferential compression as the material there is drawn radially toward the indenter. Here we see on the left crow's feet wrinkles near the eyes of an elderly person. These wrinkles form over the years because there is local compression in the skin there when a person squints or when the eyes close somewhat during smiling and laughing. On the right side, we see prominent wrinkles in the brow of a well-known shell buckling researcher. Later, you can ask me who that is. This is my 82-year-old hand, the skin of which is very, very thin, because over the years I've lost most of the fat and muscle tissue beneath it. The wrinkles radiate from the downward pressed thumb of my other hand, shown near the top center of the slide. This downward pressed thumb causes the skin to be drawn radially toward it, thus experiencing circumferential compression and wrinkling. This is a Shar-Pei dog. Its skin is so wrinkled, perhaps, because as a fetus or during its infancy, the skin grew faster than the inner tissue, giving rise to compression that caused folding, that is, large amplitude post-buckling. Folds in the crust of the earth form when one earth plate collides with another earth plate. The locally compressed crust between the two colliding plates folds as mountains build up in that region. There are buckles along the perimeter of this leaf because this perimeter grows faster than the interior region. That faster perimeter growth gives rise to compression stress parallel to the perimeter. This compression is relieved by buckling or folding. The outer parts of these vegetables grow faster than the interior parts. Buckling occurs because these outer parts become circumferentially compressed during differential growth, compression that is relieved by folding. The top row shows actual vegetables, and the bottom row shows predictions from a computerized simulation. The brain of a developing fetus and infant experiences folding in its outer regions because that region grows faster than its inner region. The folds relieve the compression that would otherwise occur there. This slide shows a piece of paper on which a pot was placed where the circular white region now exists. Liquid splashed on the brownish region, causing it to swell. The paper was locally restrained circumferentially in the neighborhood of the pot. The combination of swelling and circumferential constraint by the weight of the pot gave rise to circumferential compression in the splashed on brown region, which was relieved by local buckling. Here we have a force displacement curve for the axial crushing of a foam-filled thin-walled tube with square cross-section. The points A, B, C, D, E correspond to states in which nonlinear behavior has occurred from both large deformations and nonlinear material behavior. The states of the locally buckled foam-filled square tubes shown in green were predicted by the general purpose abacus program. And now for a few, this is not conclusions, but more comments. One, nowadays, many predictions are generated via abacus, primarily for statics problems, and Starnes, primarily for dynamics problems. Two, do the users of these very broadly applicable general purpose programs understand the physics of their problem well enough to evaluate their results? And three, will computers soon be fast enough so that no one will have to know about shell theory or buckling? Will all structures problems be solved via general three-dimensional models of solids behaving in a generally nonlinear dynamic manner with bifurcations eliminated via automatically supplied initial deformation fields or imperfections? This is Jim Starnes in 1993. And this is the end of the official part of my talk. If there's time remaining after questions from the audience, I have additional very good slides I can show.
Okay, thank you, Dave, very much. There's a lot of things that were eye-opening to me in terms of how we can see buckling in our natural world. I had one question that I had gotten earlier and was on the chat line, and it was from Dr. Raju. Dr. Raju asked, it's a two-part question. What advice would you give fresh employees in these times to, one, to become the best in their profession, and two, how do they go about choosing their mentors? This is a question that was asked. I sent you earlier. Can you comment on those?
Become the best in their profession. How do they do that? My answer, love your work, work diligently, know the field, invite experts to co-author your papers for disciplines you may be weak in, create peer-reviewed papers, write survey papers, don't rush to publish. In your papers, cite those who have significantly contributed to the field that your papers contribute to. And D, how do these youngsters go about choosing their mentors? And my answer, work with more experienced researchers. Ask others to co-author your papers. Search for the relevant literature and see whose names keep recurring. Ask others to read your papers before you submit them for publication. If there are no more questions, I will show more slides. Otherwise, I will continue to answer questions.
I don't see any other questions. Renee, do you see any other questions?
I wonder if people should understand my voice. Well, in any case, I'll continue with the slides and I'll stop whenever you want me to.
I got one question. Here, the question reads, do you recommend using simple hand calculations, conceptual design criteria as a sanity check of the Abacus and LS-DYNA computer codes?
Yes, of course. You have to have a physical feel for the problem you're solving. And in general, problems are very complex with lots of loads and lots of kinds of deformations and failures. A simple model will tell you you're on the right track.
Okay. One of the other people said you are very clear and easy to understand.
Oh, thank you. I'm very glad to hear that. Thank you.
Other people have also said that.
Thank you. I thought without questions, it meant people did not understand.
That last question was from Mr. or Dr. Professor, I don't know, Eugene Fleeman. I don't know that person. He looks like he's in our category. And there was a question from Brian Mason, a comment. He said, hopefully we can reverse the tide of young engineers treating analysis codes as black boxes without some basic understanding of the physics. They just get the wrong answers faster. That was a comment.
That's a good comment. Thank you for it. I agree.
Here's another comment from Alex. So I can't pronounce the last name. I never could, even at Clemson. Can you talk about a tough problem you have solved in your experience?
Oh. Well, right off the top of my head, I don't think of anything, but they were all tough. Let's see. I think One of them was, I think one of my programs was used to help design that large brown tank in the space shuttle, you know, the one in the middle between the two
Yes,
solid boosters.
yes.
There were difficulties there because the geometry was, well, it was a stiffened, as I remember, internally stiffened cylindrical shell. The stiffeners were kind of flat, you know. In the buckling mode, they could their cross sections could deform because they were wide and thinner than what you think of as a stiffener, which you think of something sticking out from the shell, whereas these were flattened sections, but they were thickened sections.
Okay. Here's another question from Masood Riaz Rahani. With all the progress made in this area, what do you consider to be as remaining problems or challenges?
I don't know. I think this interesting area is sort of clear from my presentation that I'm quite interested in it, is buckling of soft structures. I mean, the phenomenon is still buckling, and the structures in some cases they are shells that are thin-walled, but in other cases it's questionable whether they're thin-walled shells, like buckling of arteries and veins, which are soft and the material properties are somewhat mysterious. So further research in that area, or like really biological simulations or biological structures simulations as an area.
Here is another question.
Another thing is optimization. Optimization can take a lot of time. So how elaborate are you going to have your structure if you want to do thousands and thousands of analyses to get an optimum design? So that's kind of a question. You have to be clever about what you include and what you neglect in order to get a decent optimum design.
Okay.
Sorry, I interrupted you.
I interrupted you. Here's a question. It's to you and probably may also be to Bill, your son, from Zahir Satoda. Sorry, I apologize if I mispronounce these names. Can you tell us about the collaboration with your son, how it came about, and a memory you can share with us about working with your son?
Yeah, well, it was very pleasurable always. And we fit together like a puzzle pieces. We really are a team because Bill is not at all mystified by the computer science part of it. Like, how do you set up a website, for instance? And how do you make it appealing? And I have no knowledge about how to do that whatsoever. My knowledge is in, well, what papers or abstracts, what citations should I include in galleries of pictures, what pictures of buckled and vibrating and shells and soft structures should I include, that sort of thing. But he's very good in the areas that I lack knowledge in. So we're an excellent team. We work together very, very well.
Great. Another question from Chris S. Comments, you have an amazing passion for your work. It's very inspiring. What triggered your interest in buckling?
When I started work at Lockheed, it was before it was Lockheed Martin. This was in 1961. The first problems that I was on a team to help solve had to do with buckling of shells. And at the same time, I was attending Stanford, taking courses at Stanford, and these courses were sponsored by Lockheed. And I chose an advisor, Nicholas Hoff, and his primary interest during those years was also buckling, also creep, but mainly buckling of cylindrical shells.
Okay. Christy Stefanovic asked a question. Can we email you via the website with general questions? I'm very curious about this, but don't know how to exactly formulate one chat question.
Oh, yes, my email address is given in the website, so you can do that, but please don't abuse the privilege and make your questions easy to answer instead of difficult.
Okay. Here's a question from Sachi Caterman. Sorry, Sachi. You developed some excellent preliminary design, shell design codes at a time when finite element analysis was not as developed or was computationally expensive. What were things you wished you had considered? What were things you wished you had still continued to develop in those codes to supplement or aid modeling decisions for finite element models?
Hi, Sachi. Hi, Sachi. How are you? I guess he doesn't. He said, can he hear me?
Hi, Dave. I'm doing well. Thank you.
Oh, good, Sachi.
Good to see you.
I don't know what's happened. What happened really is that the finite elements development of the methods and mainly the speed of computers overtook the programs I wrote and made them obsolete. So, by the way, I no longer have these programs, and I do not, I cannot supply them to people who want them. But I consider them obsolete because the computers have become so fast. I don't know. That probably didn't answer your question. Sort of a political answer. Where have you gone, Norm?
Okay, here's another question. This is from Kumar Bhatia. Could you please comment on the state of global buckling prediction accuracy for large, long airplane fuselages?
I don't know the answer to that because, at least off the top of my head, I don't. I'm sure there are papers listed in the bibliography part that touch on that. But usually I would say large, long, reticulated, like stiffened structures like fuselages stiffened by wings and stringers. I think it's best to do multiple models and optimize with constraints from multiple models. For instance, in one model, the stiffeners would be smeared out, and that would pretty much cover general buckling. And other models would take unit sections in which you include just a few rings and a few stringers with proper boundary, perhaps symmetry boundary conditions, so you would get more local behavior. And you might even have a third model which concentrates on just the portion of skin between one stringer and one ring with proper symmetry conditions to get really local behavior. Of course, all this depends on how fast computers get really fast, and you can include everything in a big elaborate model with millions of degrees of freedom. I don't know how long it will take for that to happen. You still have to have a physical feel for what's going on. But right now, I've been retired for some years, so I really don't know how much practically of a long, complex, like stringer and ring stiffened fuselage and windows and all the rest of it, how much of that can you include in one model nowadays with computers? You probably have to economize somewhere.
Yes. I'll ask one of my questions that I sent to you, Dave. That was, what advice would you offer shell analysts related to understanding and interpreting the results of their detailed analyses, sometimes called the high fidelity analyses? I sent this to you earlier, the first one.
Yes, thank you, Norm. I would say have a good physical intuition about what the behavior should be. Create or find results from simpler models and compare those results with the predictions from your elaborate model. Tinker with your model by changing some parameters, rerunning, and comparing results. Try optimizing. If your model is missing something important, you may get an absurd optimum design that will reveal what you have missed.
Okay, thank you. I don't see any more questions.
Oh, good. I'd really like to show some of these other slides if there's time.
Renee, is there time to continue with all the other charts?
Yeah, definitely.
Okay, go ahead, Dave. Thank you very much. And if we run out of time, I do appreciate those that have logged on and listened to Dave. I think it's been a very comprehensive lecture and walk down memory lane. I would encourage each of you to log on to that shellbuckling.com website. There is a treasure trove of information and history there that will help each of us as we move forward. Okay, thank you, Dave.
Thank you, Norm. All right, next slide. And just stop me whenever I run out of time, okay, Norm? I don't think you can hear me.
Yes, sir, I heard you. I was on mute.
Oh, okay. Here we see post-buckled shells experiencing very large deformations. These are the types of results that can be obtained with Abacus and LS-DYNA. The top row shows axial crushing of a can. The bottom row shows a prediction of large deformation of an inflating automotive airbag. This slide shows 4 views of 2 impacting thin wall tubes. The tubes undergo very large deformations and complex changing contact conditions. Again, this is the kind of problem that can be solved with either of the general purpose programs, Abacus or LS-DYNA. This slide shows large deformations of cellular foam under a vertical crushing load. The foam consists of complicated assemblage of thin-walled elements. These very thin-walled stainless steel wine tanks at the Renty Brothers winery buckled during an earthquake in 1989 in Northern California. The loading in the tank walls with static hoop tension from the internal hydrostatic pressure from the wine in the tank, combined with dynamic axial compression and in-plane shear from the overturning moment caused by the horizontal component of the earthquake ground motion. This slide shows what is often called a bilayer, a thin, relatively stiff film, the blue color, attached to a compliant substrate, the white part. If the bilayer is horizontally compressed, as shown in B through D, the thin film can wrinkle, as shown in C. Further horizontal compression leads to what is called creasing in D. It's hard to say D. There may be multiple buckling behaviors in a complex structure consisting of multiple thin-walled parts. such as in the wall of a sandwich structure. A sandwich shell has thin-walled face sheets and a core that may, for example, be composed of thin-walled cellular honeycomb construction. At the macro level, that is at the level of the entire structure, there can be buckling with long wavelengths that span the entire structure or a large part of it. At the meso level, buckling can occur with medium wavelengths of the same order as the thickness of the sandwich wall. Buckling such as wrinkling of one or more face sheets or kinking of the core. At the micro level, buckling can occur with very small wavelengths of the same order as the diameter of one of the thin-walled honeycomb cells. This slide shows kinking of an axially compressed bundle of fibers in a laminated composite shell wall. The wavelength of the kinking, which is a type of buckling, is of the same order as the thickness of the fiber bundle. If a thin-walled flat cloth is draped over a cylinder, the part of the cloth that under gravity becomes vertical wrinkles or folds because it is drawn inward to a smaller radius. The circumferential compression that would naturally result from this 90-degree rotation from horizontal to vertical is relieved by the development of folds. This slide shows an optimized axially compressed longitudinally stiffened panel. During topology optimization, the stiffeners may become tapered in the axial direction and voids may develop as shown here for the optimized middle stiffener. During the past several decades, many papers have been published on buckling of shells, the walls of which consist of what is called functionally graded material, or FGM. That is, material, the properties of which vary through the thickness of the wall of the shell in a smooth, functional way. Here's another example of a functionally graded shell wall. In this case, the density of nanotube reinforcement, indicated by black dots, varies through the wall thickness in various ways. This slide shows sectors of an annular plate, the top image on the left, and the cylindrical shell, the bottom image on the left, the walls of which have functionally graded porosity, as shown to the right. Here is a laminated composite shell wall with piezoelectric layers. The piezoelectric layers can be used as actuators and sensors to control vibration response, as shown in the next two slides. This slide shows piezoelectric actuator and sensor patches to control vibration amplitude at the tip of a vertically oriented beam. Here we see the qualitative control of the amplitude of the fundamental vibration mode at the tip of the beam by means of the piezoelectric actuators and sensors shown in the previous slide. In architecture and in aerospace applications, there exist thin-walled structures that can experience very large displacements by folding and unfolding. In aerospace applications of this type of folding and unfolding is used when packing the structure on the ground and deployment of the structure in space are required. There are many recent papers, especially in the civil engineering field, on buckling of axially compressed prismatic thin-walled columns with various cross-sections, especially columns made of cold-formed steel. One of the 11 categories of structure included on the shell buckling images page of shellbuckling.com is prismatic shells. Here's an example of what is called a stub column that consists in this example of a hollow square thin-walled steel casing filled with concrete. The specimen has been subjected to axial compression. There are many papers in the civil engineering literature on buckling of structures of this type, with various steel hollow cross-sections and various fillers. Buckling of shells and plates with lattice walls is a popular subject. Here we see an example. Here's a lattice-walled architectural structure that can be deployed to form a dome. There are many recent papers on the behavior of so-called auxetic thin-walled structures, that is, structures the walls of which have negative Poisson ratio. Walls of this type are of cellular construction. In this slide, we see two images, both showing the deformation of cellular walls under a bending moment M. The left-hand image shows the deformation of a cellular wall with a positive Poisson ratio. Bending leads to a saddle type of deformation. The right-hand image shows deformation of a cellular wall with negative Poisson ratio. The geometry of the cells differs in the two examples. This slide shows the occurrence of chaos in dynamic response. Here we see dimensionless normal deflection W over H versus dimensionless dynamic pressure lambda of a cylindrical panel in a supersonic flow. Flutter initiates at the bifurcation pressure, about lambda equals 600. The post-bifurcation flutter is initially orderly, that is, oscillatory response occurs in a single mode up to a dynamic pressure of slightly less than lambda equal 800. At that pressure and beyond, the flutter is chaotic. That is, there is oscillatory response in more than one mode, and the amplitudes of the various modes continually change with time in an unpredictable, that is, in a chaotic way. The next slide shows the dynamic response history of at a dynamic pressure of lambda equal 800, slightly higher than that at which chaotic behavior begins. Here we see the time history of the initially chaotic dynamic response, W over H, versus dimensionless time at a dimensionless dynamic pressure, lambda equal 800, just slightly above that at which chaotic behavior begins, as shown in the previous slide. The amplitude of the fluttering varies with time in a chaotic manner. The variation of chaotic amplitude with time is not overwhelmingly large in this example, because lambda equal 800 is only slightly above the value at which chaotic behavior begins. This slide shows a very popular benchmark problem, a thin-walled cylindrical shell subjected to diametrically opposed inward-directed concentrated loads. This is the so-called pinched cylinder problem. In this case, the ends of the cylinder shell are supported by rigid diaphragms. Here we see the very large deformations of the pinched cylindrical shell under increasing inward-directed concentrated loads. This slide shows the very large deformation of a pulled as opposed to pitched cylindrical shell with free ends. The left-hand image shows the prediction from a mesh-free, as opposed to finite element, a mesh-free model with 1680 points called particles by the authors. The right-hand image shows the prediction from a mesh-free model with 6,560 points. On this slide, the top image shows a curved clamped shell segment under a downward central concentrated load P. The bottom image shows convergence with total number of nodes of the predictions of normalized central normal displacement from various models. Model 1, finite element model, FEM. Models 2 and 3, finite element abacus models, that is finite element model in abacus. Number 4, EFG-MLS, which means element-free Galerkin method, that's the EFG part, with moving least squares, that's the MLS part. And 5, EFG-MK, element-free Galerkin method, that's EFG, with moving Kriging model, MK. In this particular case, the rate of convergence with increasing number of nodes is best for number 5. All right, you'll be glad to know this is the last slide. The upper part of this slide shows a graphene sheet and 3 types of single-walled carbon nanotubes made therefrom, as described earlier. The lower part of the slide lists free vibration frequencies from a semi-analytical method and from the finite element method for one of the single-walled carbon nanotubes shown on the right. The free vibration frequencies depend strongly on the non-local parameter mu, various values of which are listed in the table. Non-local elasticity theory was developed by Erringen in 1983. This concludes my presentation. Many thanks for your interest in buckling of shells, and thank you, Dr. Norm Knight, for chairing the session. And thanks again to AIAA for setting up this special session.
Well, thank you, Dave. Maybe you could stop sharing your screen and we could, you would see who might be on. If you can do that.
I better open up this thing. Start video. How do I turn on the camera, Bill? The camera is off. Bill, are you there, Bill?
Yeah, towards the bottom of your screen, there should be stop video or start. There you go. We can see you.
Actually, no, is the video, okay. And what about all the audience? Do their pictures exist?
I don't know if they'll turn themselves on or not. There's.
Oh, there's one. Hi, Sachi.
Hi, Bill.
There's Mr. Fleeman, Sachi, Raju, Don, Carlos.
Oh, I have to hit this. Oh, good. I hit this arrow and more people come up. How do you do, everybody? Thank you. Hello, Don Phillips. Nice to see you.
Thank you, Dave.
Hi, Carlos.
Congratulations again on the award.
Hello, Kiera. How are you, Kiera?
Fine, thank you. It was really inspiring lectures. Thanks.
No, thank you for attending. Nice to see you. Brian Mason. Hi, Tricia. Thank you for coming, and thanks also for the award celebration yesterday.
Oh, you are quite welcome.
Hello,
Congratulations.
Arian. Oh, thank you again.
Aaron,
Aaron,
you're on mute. Aaron,
Aaron,
you're
you're
mute.
muted.
Arian, you're
You're
on mute.
muted.
On mute. We couldn't hear you.
Thanks,
There you go.
Dave, and hi Eugene from your days at Georgia Tech. And David, this is fantastic talk. Paul Weaver,
Oh,
you have a beard now.
you're very kind. Thank you so much. You know, your kind comments motivate me to continue this work.
Please do, please do. There is no end to it.
Yeah, that is a true comment. And I find that when they get up at 3 in the morning and do things, it's a huge field. That's the problem. I thought I was getting into something much smaller.
Yeah. By the way, I had the pleasure to meet Nicholas Hoff in 1982. He was getting at Georgia Tech the Money A First Award. So I got to meet with him, Larry Rayfield, George Simitzis, and a group that you know very well.
Ah, good. Well, Nick died at 90.
Yeah.
A little over 90.
So Dave, can I just ask, after I congratulate you again, I'm dying to know who the wrinkled faces were in your original presentation.
There were 2 wrinkled faces, that with a crow's feet around the eyes, whose name I don't know. And the other, I don't know whether he wants me to tell who he is. How much do you want to know this? How much are you willing to pay?
Oh.
I've given enough publicity to showbuckling.com, I tell you. Which is
Oh, I see. A bargainer we have here.
It was my forehead. I told Dave it was my forehead from the lab whenever I would do a buckling prediction and it would miss. I would frown.
That gives a whole new meaning to a post-buckling defamation, I guess. But
Yeah.
Yeah, this whole area of buckling of soft structures, like biological models primarily, is it's interesting. There's a lot of papers in a journal called Soft Structures.
Yeah, fantastic. So you see, Dave, you've gathered around you all friends, and David, Mark, how are you? Mark Schultz, how are you?
Yeah, Mark, welcome, man.
Mark.
Long time haven't seen you.
Yes.
Hi, Mark. You're at NASA, right?
That's right. Congratulations again. I enjoyed your talk.
Thank
Yes.
you, Mark.
Dave, in soft tissues, I think one of the challenges is to ascertain what are the local properties
Exactly.
to measure them and the aging process.
Yes, yes, that's, I mean, it's much more difficult than metallic or even
Yeah.
composite material.
Okay, any other comments or questions for Dave?
Yeah, just thank him again. It was great, Dave.
Yeah, thank you very much, Dave. I appreciate it.
Thank you,
all
Dave.
very kind.
And just a comment between you and Bill. What a great relationship there. Go and enjoy that. That's really wonderful.
Oh yeah, we've been at it since 2011. And it's been a wonderful time, and it will continue. I plan to live at least to 100. Knock wood.
There you go.
But
Dave, I thought it went way. I thought the collaboration went way back when there was a paper with Bushnell and Bushnell. Way
Oh
back.
yes, yeah, it wasn't on the website that time, but yes, Bill,
Yeah.
Bill and I. Bill worked at Lockheed for 5 years, and during that time, he and I worked together on some things.
98.
Also
So,
worked with
so-
Charles Rankin on Stags.
Sachi, that's right. I remember that. Bushnell, that's right.
Yeah.
So there you go.
goes way back.
Excellent.
May the academic DNA endure.
Okay,
Well, thank you all for coming. Thank you all for attending and listening so patiently.
and thank you, Dave.
Thanks,
Again,
David.
Thank
Thank you, David.
Thank you.
Thanks,
David.
Norm.
Thanks.
Thanks,
You're
Norm,
welcome.
for the
Yeah, Norm,
news.
thank you so
Norm,
much.
You're
for
welcome.
chairing the
Great
session.
handling.
Thanks, Lehman.
Bye-bye.
Okay, bye,
All right,
everybody.
cheers.
Bye-bye.
Take care.
You. Bye.
Bye-bye. Nice to see you all.
Bye, Tricia.
Well, Norm, thank you so much.
You're quite welcome, Dave.
You did a wonderful job. I almost forgot to give you a chance to give your introduction. That was really good.
It all worked out. And the comments that are on, that came in through the chat, I saved those and will email them to you.
Oh, thank you.
And you can read them and do what you need or not.
Thank you. You've been a wonderful chairperson and a wonderful friend. One can't expect a better friend, really.
Well, I don't know. And Bill, it looks, I've never met you. You look different than the picture on the hike.
The picture was taken quite a while ago, so I've lost a bit of hair since then.
We all have. We're all getting that way. So, okay, well, I
Okay,
guess
Norm.
we're done. Anybody, there's a few people still on. Raju, did you want to say anything or?
Where's Raju? I didn't see his picture.
It's the RAJA.
Oh, Raja, not Raju.
Yeah,
Oh, okay,
I
sorry.
think that's him. Kevin Rivers, Jonathan.
Well,
Anyway.
goodbye, everybody, and thank you.
Okay, we'll see
Thanks
you.
so much. Norm.